in curves. No organic molecules, or not many. What else will there be? Not much hard fact. Just I'm going to ask a question and then give a very, very naive, which I expect to be completely wrong, possible explanation. So what to begin, let me go right back to the beginning. Biology is homo caro. I think we all agree on that. My definition is a little different than everybody else's. It just says the mirror image of biology does not operate. And that allows for a mirror image of complicated reactions as well as just individual molecules. So I think that's probably controversial. Let's just show a few things, therefore, that don't exist in nature to show you what you mean by homochirality. Some mirror image biological systems do not exist in nature. That one doesn't exist in nature, nor does that one. The first two on the right don't exist because I simply took the ones that do and mirror imaged them on the computer. And those do not exist. They've got the wrong chirality, wrong handedness, wrong twist. The one on the left is actually a little bit more interesting. That doesn't exist either, except in some people's laboratories. Well, this picture doesn't exist because it's got the wrong handedness for the DNA. Interestingly, that actually was what, not reversed by me, was what actually is given to the students on this study card at CU Bookshop. Now, you can ask what CU means, and that is not Cambridge University. They do know about DNA. It's not Copenhagen University either. Whether they know about DNA or not, I don't know, but it isn't. I'm afraid it's my second home after I retired from Oxford, which is the University of Colorado, which certainly knows about DNA and RNA and the handedness, but apparently the teachers don't. Anyway, that's what the students are taught in CU. So I don't want to belabor that, but just to make the point that the mirror image does not exist. Remind you that this is a curve. I don't know how well you can see the helix going around. One of these helixes regularly exists. The other one actually, as we'll see in a moment, exists in laboratories, but not in nature. And likewise, we've had this picture in all the publicity for the meeting, and many, many times, many speakers have used it. But I wanted to make the point that there are the two separate systems of handedness, and in general, now this is a hypothesis. I'm not even sure. There may be that people will point out exceptions. But there seem to be two groups of molecules, each with a single coupled together handedness. Now there may be more, and I'm not expert enough to know, chiral molecules in nature, whose chirality is absolutely, essentially locked into both amino acids and into sugars and RNA, but I don't know of them. But following the talk this morning, there may well be, because of all this asymmetric catalysis that was going on between amino acids and sugars, and so it'd be interesting to see whether there are such molecules that absolutely lock the two systems together. Because my talk is about the locking of the two systems, and that's nature's system. There's a mirror image system which is not found in nature but has been made in Japan primarily. And there's a quote there to a very beautiful experiment where they had reversed nucleic acid interacting with reversed proteins and acting in a way that you would expect, a reversed way. So that absolute mirror image I'm not interested in, because they've got the same relative handedness. What I'm interested in is these two other possibilities, which are logical if not actually physical. LL and a DD, a world where L sugar and L amino acids or D sugar and D amino acids. And I've called those reversed relative handedness, just for short, RRH, all through the talk. And my question, which I'm posing in this talk, is: could this happen? Was there some absolute requirement that it didn't happen for us? Could it happen somewhere else in the universe? Could we make it happen in a laboratory, possibly? So many people here. If you ask the average, at least if I ask the average organic chemist, say it's totally impossible. Then you press it a little bit, and it becomes not quite so clear at what point it became impossible and why is it impossible. So let's look at that, and I hope that I had to learn a lot from this meeting. Possible obstacles to having that. Well, obviously the 2 points at which this matters most are the initial choice of the relative sign, the point at which nucleic acids and the amino acids bifurcate. Now, it is my thesis that they might have bifurcated separately, and there might be, or might not be, a coupling between the bifurcations. Of course, if you have a model of the origin of life where both nucleic acids and proteins and amino acids sort of form and bifurcate simultaneously, then this doesn't quite work. Then one has to have some understanding of the coupling that was going on at that time. But if you think one going before the other, then presumably the first will bifurcate into homochirality, and then will or will not influence the second one coming along. Because I come from Colorado, where it's a sort of gospel truth, my viewpoint, which I understand better, is the RNA world, where the RNA comes first, bifurcates. Quite a long time after that, proteins and amino acids, proteins in particular, are generated as a mechanism for doing so evolves. And so that there is the possibility of 2 separate bifurcations, which could or could not be absolutely coupled. So one possibility definitely is that once you've fixed the handedness of, say, the RNA, then you haven't got any choice. That's going to force the handedness of the amino acids and proteins. But that is not by any means a given, it's a possibility. And second is that there's some absolute biochemical incompatibility between these mixed handednesses of the sort that was being discussed in the previous lecture, where it was rather clear that the amino acids tend to catalyze one sugar, the correct one, luckily. And if that's an absolutely crucial part of biochemistry of life, then this whole thing falls together to ground, because the subsequent, they are biochemically incompatible. They have mixed handedness. But another more macroscopic possibility is something like the fact that LDNA and L helices, L alpha helices for the proteins, they have the same handedness, and if that were important, then you would get locked between the handedness of the 2 systems. But I haven't seen any biochemical or biological paper that says that they are locked. I mean, it's an interesting phenomenon that they're the same, but not necessarily of biological significance. I don't know, but somebody may be able to help them. So let's look at protein handedness in an RNA world. Homochiral RNA came first. This is just obviously one model, but I hate to make these discussions in a complete vacuum of models. I like to have some sort of picture, right or wrong, of how things developed, and so I then asked how chirality developed in that picture. Of course, if the picture is wrong, then it has to go back to square one. So my view of things is that the RNA came first, then gradually developed a translation procedure, crude at first for proteins, very crude at first, in which originally the handedness of the amino acids was not selected, but only as the translation process got good enough to select individual amino acids did it actually get good enough to select the enantiomer of the amino acids, because the enantiomer is at least as difficult to select as the individuals. Now, there's a lot of reasons why you want if you're doing that, you do tend towards homochirality. You get in effect a bifurcation, but it doesn't quite look like a bifurcation, because it's the result of more and more efficient protein synthesis and being developed by the natural processes. And I just put a few pictures because people don't like writing in their pictures, but they're not really of any significance. Just the three areas at least where it is advantageous to have homochirality in translation. There's polymer formation, folding efficiency, and enzyme structures. Particularly enzyme structures don't work very well if you're very far from homochirality. So there's a lot of pressure on the whole system to get homochiral. The question is, with what handedness did the homochirality that is formed this way take? And so let's move on now to initial choice. Now there's two possibilities. One is that it's not coupled to the RNA. In other words, there's a second bifurcation which just gives either handedness, possibly randomly or possibly determined by other things than the RNA. And I don't want to go into those, but these are all various sorts of handedness determining factors that have been put forward. There are of course others. Chance is my preferred one, but not necessarily statistical chance, but the sort of statistical fluctuations that have been talked about at this conference, and we'll be talking about. So, if that were the case, then the protein handedness protein amino acids would become homochiral, but the handedness of it would be unrelated to, it might be fixed, but would not be necessarily coupled to the RNA. So if the RNA bifurcation originally went the other way, then there would be the opposite handedness, and you would have the RRH possibility. That's one obvious possibility. The other possibility is that it is coupled to the RNA, and if so, one has to think a little bit about how that would happen. Quite a lot of work has been done. I just put it down, some of it, it's not by any means all of it. The arguments about geometric fitting and so on, that one-handedness fits better. People have looked at reactions. There's quite a nice paper a few years ago on a mini helix, which prefers an L amino acid, but it's likely that the selectivity is on some sort of tRNA or proto-tRNA, and so it's interesting to look at that, and that's been looked at, and it's not very, well, it is quite often stereoselective, but different types of reaction and different amino acids give different answers. So there's nothing that sort of jumps out, that everything goes the correct way. A very interesting thing, at least from my point of view, is this third one, discovered by my co-worker Mike Yaros. Well, he's the boss of the group that I work with in Boulder, Colorado, and he discovered that there's a very strong binding site for the amino acid in small RNAs, and it only binds the L arginine, which is quite interesting. But then other people found other binding sites which bind the other handedness, and it's by no means clear cut, but there's a strong preference for one. So I suggested that my only contribution to this field was that he's an expert in artificial evolution, making RNAs by cyclic evolution, artificial evolution in the laboratory, which do particular things. And my suggestion was that he take a racemic pool of amino acids and recycle the RNA to bind to some amino acid and see which one it bound to, because that's somewhat like nature, possibly. They've been working at, so that's a hard experiment. Because, of course, the difficulty is that in artificial evolution they only have one-handedness of the RNA. You cannot do artificial evolution with L-RNA because companies won't supply quantities of L-RNA that ruins their apparatus. So you can't get it to do it, and so you have to use the regular. And you also there are biological processes in evolving this RNA, which are use biological materials which are one-handedness. So it's a difficult experiment to do, and I'm afraid that I can't report a conclusive result. It's they find lots and lots of binding sites, some of them on the left and some of them on the right, and some of them are strong and some of them are weak, and some of them are there for one amino acid and some for another. So the fact is that there is nothing absolutely conclusive. The answer I expected they might find was that all the strong ones were for L amino acids, say, and then that would be quite interesting. But actually that isn't the case, and no conclusive result. And also the experiments are not absolutely reproducible either. So what I would conclude this part of the talk is that the choice of L protein may be due to coupling with DNA, but I believe we cannot absolutely rule out, and I'd be very interested to hear people who disagree with this, that our world might have had RH, another world might have reverse relative handedness, or somehow we could induce important systems that have had that. Very simple systems have been constructed with it. So that's sort of the first phase of the talk is it possible to have reverse relative handedness? The second is that I'm not sure that we know enough to absolutely rule it out, although some of the things in the talk this morning worried me, because there was a lot of coupling between amino acid chirality and sugar chirality, and it may be that those are crucial enough in biology that they do rule out mixed handedness, but we can discuss that afterwards. Worth further investigation is all I would say. I don't hold to this as an absolute thesis, but I just hold that it's not completely stupid thesis. So let's look at biochemistry. Now this is where I clearly get out of my depth, and I saw that this morning in particular. Clearly, we're only interested in nucleic acid protein interactions, or sugar and amino acid interactions, because internally you can reverse the sign and everything goes in a mirror symmetric way. If you change all the amino acids and all the proteins, then protein-protein effects are fine still, and likewise nucleic acid effects. It's when you get the coupling between the two that you've got to worry. So when one's thinking about this, one can either reverse the L, the DNA, or one can reverse the amino acid protein element. I usually find it easier to just reverse the DNA element and leave the protein amino acid element the same, because we're all familiar with what that looks like, and it's very easy to give a picture of a wrong-handed RNA or DNA. So I tend to do that. But both are known in the laboratory. Both LDNA has been made and characterized, and it works like it should. D and D proteins have been, or A D protein has been made, and that works as you expect it to. And as I showed in the previous reference, there's actually an experiment with both reversed together, and that works exactly as you expect it to. But nobody has yet done an experiment on a mixed-handed. They could have done, but they haven't. In other words, no one's taken the LDNA and had to go at it in detail against regular proteins or vice versa. Well, this is where I get totally out of my depth. I divided the systems into small systems and big systems, but I've really left out, I'm really talking about enzymes here rather than the small molecule interactions that we talked about earlier, and I have to rethink a bit this slide in those terms. But anyway, my Bible on this is this paper by Lambs in 1995, who deals with how nature deals with the wrong-handedness of left or right. And basically, well-known observation that you need at least 3 significant points of contact to get a chiral identification. In the inversion, at least in the sort of protein world, is done by a geometric arrangement of the catalytic residues. There, in other words, the whole structure of the protein changes to give you a mirror image position of the catalytic residues. But they're the same catalytic residues, of course, in the one-handed world. They're often widely spaced on the protein chain and only come together in their catalytic chiral form after folding. Normal L proteins have no difficulty in producing sites of either handedness, because they're both due to a global structure of the protein with the particular catalytic amino acids being in odd points on the chain. And finally, equivalent sites can often be formed in more than one way, because what you're doing is you've got to make a protein that folds into a structure which gives these catalytic amino acids, gets them into the right triangular or higher order chiral distribution. And the typical books on particular protein structure show you how that happens in cases where nature wants to deal with left and right-handed small molecules. So this may seem rather hard for people who worked all their lives to deal with chirality, but in a certain sense, biochemistry does deal with chirality in much the same way as it deals with anything else. It's part of the chemistry. So what about large structures? Well, I don't know if you can see that large structure, but there's a DNA there and a large protein ball around it, which is fitting pretty closely to it, and obviously and is crucial to what's going on. And clearly, it's got this protein ball has got to fit the chirality of this DNA quite nicely, and there's no doubt that the protein that fits it like a glove and works very, very closely with it. And the question which we have to ask is, if we kept the proteins the same, but reversed the handedness of the DNA, in other words, we go to a mixed system, RRH system, how would nature cope? Well, you could argue, and I think the immediate answer of many biochemists and biologists is that it just wouldn't. It couldn't. I mean, it's completely, the coupling would not fit at all. And that's true. It simply would not work. But that isn't really the right answer, because you have to ask, how did this all come about? And it came about by slow evolution from much simpler systems and much simpler operations. And nature didn't just suddenly dream up this big protein here, which fits exactly into all the grooves of the nucleic acid. It happened slowly by evolution, chemical evolution, over all sorts of intermediates and and worse solutions and better solutions and so on and so forth. You're all familiar with chemical evolution, I expect. And so what is actually the crucial answer is here, is that if evolution can find a protein to fit this one, is there any obvious reason why it couldn't, starting from scratch again, find the other one? Another one which fits the reversed DNA. And I see myself no reason why it shouldn't be able to. It's hard enough to see how it did it in the first place, but it's no harder to see how it did it in the reverse case. So that's what I would hypothesize and be shot down. So in an RRH world, the handedness of individual nucleic acids plays a relatively small part. It's not crucial to the details, except in sort of small. It determines the gross handednesses, but for the most part, it isn't very significant. In other words, the handedness of individual amino acids in an enzyme doesn't really matter all that much, I would argue. So, if we had an RRH world and it was able to get started, then presumably chemical evolution would develop along fairly familiar lines. Somewhat similar biochemistry. The individual molecules would look a bit different, but actually probably we get the same set, and they would probably be somewhat related, but not identical clearly, because they've got to deal with an opposite-handed RNA and DNA. So, having got that far, what about subsequent evolution and complex life? I'm really going way out of anything that I know anything about. But let's just hypothesize that it did all work, it did develop. What would life be like? Would it be completely different? Would we be here? Would we so on? Well, that's something we can't say, but I expect everybody is aware that there's a lot of discussion in literature and books about a rerun of the experiment of life. What would have happened? What would happen if we started off on either on Earth or somewhere else and reran everything? Presumably we get life. How similar would the life be to what we've actually got? And there are two rather different viewpoints which are characterized by the two books which discuss this, and I don't think it's known what happened here to us, which of these were true. But basically, taking Conway Morris and a very nice book, Life Solutions, he says that evolution is highly convergent. This phase space, if you like, of the results are quite constrained. And although evolution is buffeted around and goes in lots of divergent paths, it has in fact a fairly small number of workable solutions. And it's relatively convergent. He even argues that there would be intelligence and human-like life. I don't know I go that far, but he says it's really quite convergent, and his book is full of examples where things like some eyes and all sorts of biochemical processes converge from different sources in nature to very, very similar results. The other, sorry, what was I going to say? The other, completely opposite viewpoint is from Gould, in Wonderful Life, and of course lots of other places. He says that evolution is highly dependent on the details of what actually happens to you, like meteorites and the details of how your oxygen changes and so stuff like that. And he just claims that the outcome is completely different, and you can't really say, if you rerun the experiment, you get a completely different answer. And in between those, you can have your own views. But there are two sort of end point arguments which are quite different. What has that got to do with us? Well, if there were RRH life, of course the way it developed would be effectively a rerun. So the RRH is a rerun. Let me just show. Sorry. I've lost the slide. Lost it. I'll work on my machine, I think. I've lost the slide like many. Sorry about that. I don't know why. Some reason it doesn't want to find itself. Computer's taken over. Sorry about this. It wants to do something that I don't want to do. Can I get rid of it by just pushing it down to the bottom or something? Okay, got it. This is just a very simple-minded schematic of evolution. There you are. There's the whole of Darwin and everybody else all in one plot. A sort of a semi-random walk from t equals 0 to a final Earth. And that's what we are. We're on that black line. We are the black line. Now, Conway Stewart says that it'll be pretty close all the way along because the solutions that can be found are quite close and strongly influenced, and so the whole of the play will be somewhat similar. Gould, on the other hand, says it's quite different. That's just a schematic of what the previous slide said. Well, all I can say about an RRH one is that there's two possibilities. They'll be pretty similar because the biochemistry is pretty similar, or wildly different because the circumstances will be different, and maybe the fact that the relative handedness is different has a crucial effect at some point. Probably not. It's probably going to be nature again. Now you've got to be there's a little subtlety here about what you mean by a rerun of the experiment. Do you mean a rerun on Earth as Earth was? In which case the Gould contingencies might all be the same. So there are subtleties about what you mean by a rerun, which are not always spelt out in the literature. But anyway, basically Gould means on a different planet and a different time with different meteorites hitting at different times and different temperature changes from the sun and so on and so forth. Everything can be different, and different probably mineral compositions and what have you. Well, all we can say is that the conclusion of what RRH life might be like is that we don't know, but the fact that it's RRH, the biochemistry is relatively reversed, might actually be less important than what went on anyway. And so we might be quite similar, even if we had RRH molecules in our body, or we might be different. I don't know. My conclusion I believe that there's no absolutely conclusive evidence, and I'd be happy to hear some there is, that it could not, that the RRH could not occur. If it did occur, it would be likely to be rather similar to our familiar one, with some obvious necessary changes, but not vastly different. And life, RRH life, could be expected to be as similar to our own as repeated experiments with the same handedness, with our own handedness. In other words, it's likely to not be wildly different, is the hypothesis either. And so, sit down, I have raised the question, is there an absolute argument against RRH life? And if not, what would it be like? I don't know. These are just wild hypotheses, wild guessing. And that seems to me something that one's allowed to do in this sort of meeting, which perhaps referees in papers don't like too much, and more formal meetings don't like much either. Thank you very much.
Thank you very much. We'll start the discussion. Yes.
Is there a reason other than parsimony to think that if the nucleic acids and amino acids are not tightly coupled to one another, they might each be tightly coupled to some third system that causes them to have?
It's possible, but we don't know. I don't know the third system. I mean, it's a hypothesis which may actually not be totally correct. There are two systems. Because there are obvious interactions between the systems, as shown in small molecules, at any rate, this morning.
You mentioned the possibility of coupling by one paper by absorption
on the surface.
Yes.
Yeah.
There is another possibility also to have coupling. It is that the RNA interact with some urous acid, mechanisms give a urous acid which induce symmetric reactions. There were some experiments, for example, having Feringa.
Yes. Now, I've got a lot more possibilities. Well, there's also just the Pizzarello fact that amino acids do seem to produce chiral sugar in a very simple, straightforward way. But whether that is a real, absolute, essential coupling is not clear to me. It does form a relationship which one has to worry about. So.
I think if you have the evolution of life,
Sorry?
if you regard the evolution of life, you may have the conventional system, which we know, and your RRH system.
Yes.
And I think these compete with each other. There's a really competition, and if one of the systems is more effective, for example, because the chemical reactions are more effective, you will always get only one of these systems.
That's true if you ever get to two systems. I think early bifurcation tends to say you're going to need one system fairly early on. I mean, everyone assumes that you don't have pools of left RNA and the RNA in different places, or even intertwined. I mean, the question why you need bifurcation, why you need homochirality, I don't think has actually been. I mean, it's just more efficient, isn't it? It's not necessary. It's more efficient. I mean,
there is a question. What do you think about? Because if you don't have chirality, you have such a disorder, all the possible.
Not necessarily.
Outcome.
Not necessarily, because let us say that well, you've got to think of how the sugars are made. But let us think about amino acids being made. Okay? How would you have two systems? The answer is that you'd have twice as many codons in your in your genetic code. And half of them would be for one-handedness, and the other half would be for the other. And you would have proteins coded to be single-handed, other proteins to be coded to be the opposite hand. And it's not, there's been a very interesting paper, I think, by a man called Hack, H-A-A-C-K, who looks into all the different possibilities of the proteins that you can make where you've got both handednesses as a polymer. And you can make all sorts of, a lot more possibilities than with single protein, because you can have domains that are different handedness, you can have even sequences of half a domain, you can have complete proteins joined together, multi-proteins, one-handedness and the other, and so on. And he says, why did nature not do that? Because it's obviously much more powerful. But of course, it's also much more complicated. And if you have sort of parsimony and simplicity as being part of the efficiency, then that might be the reason. That's what he says. Because he's really interested in drug companies doing this. And he says, why didn't nature do it? And the answer is, it can't be because the end result is worse, only that the means get too difficult. So maybe that's the reason why. The other question is, can you have domains? In other words, I mean, people still looked, didn't they, when these first samples from the black smokers down the bottom of the field of the ocean, they did wonder whether that was the same. And certainly when we go to Mars, or wherever, one of the first things one hopes will be looked at is the chirality.
Since the crystal structure of the ribosomes are known today, have somebody tried to see whether they could put some the deamino acid within the channels of the ribosome?
Well, what has been looked at in quite a lot of detail is take a regular or simplified ribosome and try and get it to incorporate a deamino acid into a chain. And that you can get quite far. You can get the transfer RNA and all the proteins that go with that. You can get them to reverse quite well. And once it's in the ribosome, it doesn't actually, the main part of it doesn't care. It works perfectly well with a reverse. It doesn't, there's not enough structural difference because it has to work on all the amino acids without too much differentiation. It doesn't actually differentiate the anatomies. However, there are specialized features in the movement of the amino acids into the right place and things like that, which actually do discriminate. So you can't make the regular process to incorporate the wrong ones. To incorporate the wrong ones, you have to either make ad novo and specify what the handed, and people put the wrong handedness into protein chains quite regularly. And of course, nature does that, but nature always does it by sometimes just by racemizing sometimes by having a transfer of handedness.
The second question is, you pointed out that the RNA was formed before.
Well, it might be.
But I think today, as you have said, to build up an RNA molecule is much more difficult than to assemble a Boeing 77 in a junkyard.
I don't believe
and I think that the community, and I think more and more people now in the field,
they don't think
that RNA evolved after.
It's possible, but not for the reasons that you gave. I mean, it's nothing like that. If you wanted to make a Boeing 777 and you had a junkyard.
No, I think it's a prebiotic.
If Ford could make a musical orchestra out of its Ford Focus, which you can see on the television every day now. No, I mean, I'm joking, but what you can do with sequential improving evolution is quite different than what you do if you look at as it were, a junkyard. So I mean, it may be that you're right, but people have quite specific ideas, many of the steps of which have been carried out, haven't they? I mean, you don't start with an RNA to begin with. You possibly start with something achiral and simpler, which there are many suggestions. And you build up something that likes to make a polymer, and that preferably, in my view, doesn't have the chiral problem. And then that next stage begins to develop polymers with chirality, rather inefficiently to begin with, but as soon as there's some sort of feedback, it gets more efficient. And after all, RNA has these properties which that it can replicate, okay, with difficulty, and you need a bit of support, but it can do all sorts of other things. The whole start of this RNA world was the fact that an RNA can act as an enzyme, and it can do all sorts of things. And it can operate on itself, and it can operate on other systems, and almost every stage in the. I mean, I don't know all this from first hand. I know this because I live in a laboratory that does it. I live part of the time in the laboratory. I mean, almost every stage of RNA replication, for example, RNA chemistry, can be replicated without protein enzymes. So, I mean, I would like to see I think that the RNA can be shot down, but I'd like to see a step-by-step description of a non-RNA process. That's why I use RNA, because it's a lot more. If there is one in the literature, it would be very well worth knowing, where you start with whatever you like in the form of amino acids and small chemicals, and you actually develop.
Not only replicated, but how
You've got to form.
must be formed.
Yeah, you've got to form polymers. You've got to replicate. You've got to do quite a lot of things. You've got to make the molecules in the first place, some way, because you can't really, for long, use the naturally abundant ones. You run out.
Yes.
The people that run the Colorado University bookstore might have drawn some consolation from Jack Tunnis's paper about 6 or 7 years ago, where he points out that Linus Pauling's alpha helix, the original illustration of it, was the wrong enantiomer.
Yeah, I'm sure. Well, but I mean, on that point, there is a website devoted entirely to l-DNA, and it picks out all the cases, including some fancy books on biochemistry, where they have got it wrong. And there are, I mean, it has thousands of entries, and they're added to every week. Even my own university had a big poster, I noticed to my horror, on DNA engineering. And the DNA was the wrong added.
I heard a story from a colleague that it was not the error of Linus Pauling, but it was of the editor that put the
Yeah, probably. Absolutely.
No, because they're letters. It's
But it's actually quite. It's
Pauling.
If you look at the history of the famous Watson-Crick DNA, and they are not at all clued up on the handedness. I mean, they guessed it from very simple chemical considerations, and they were right, but they didn't really have any evidence at that time. So, I mean, handedness was a sort of second. I mean, they knew it was a helix, but which helix was not so clear.
So, there was an article of Hoffman and Laszlo in Levante some years ago. Hoffman and Laszlo about this type of error, and they took a very simple molecule came from. And they found that in many papers it is written in the wrong configuration. It's very easy to understand because it is copy of copy of copy.
Sure.
Nobody.
So with modern computers, it's quite easy to do a mirror, or Xerox machines. You just press the wrong button and it produces the mirror, the mirror image, and you're in real trouble.
Voilà, on a critique ça. Okay. No question? No? And thank you very much.